Hey class, we're back again, and now we have example 3, solving a capacity problem, and this is from section 8.6, so this is the last video of the series. Again, I'll make mention that I'm doing this up in the third floor study zone, and if there is an interruption or an announcement, I'm just going to keep going with that. I'm also not sure if you can hear the pipe noise in the background, but some of the pipes in the school tend to get kind of noisy, so I apologize if that's causing any interference. So let's look at this capacity problem. It's saying here that we've got basically two oil tanks and they're spherical and that they're being filled. And so we're assuming that those two spheres are similar. I mean, all spheres technically are similar, but that's just something that's not stated, but you guys can assume that. So it says that the smaller tank in the photograph has a capacity of 1,400 meters cubed. The larger tank has a capacity of 4,725 meters cubed. It says during the refining process, both tanks are filled with oil from a pumping station, and the key thing here is that they're being filled at the same rate. So if they're being filled at the same rate, then we can figure out how many times longer it will take the larger tank than it will take to fill the smaller tank. And so notice they said how many times, kind of awkward. They're not looking for an actual measurement of time, because then we'd actually have to know something about our rate. But what we can do is we're going to set it up just to think the times, if we want to call it that, kind of how they've indicated it. We can figure out the ratio between these two things. And so we'd say 4,725, and that's meters cubed. And we're going to divide that by 1,400 meters cubed. And that's going to come back to give me 3.375. And again, that's telling me how many times it's this many times longer, if you want to use those words in their problem. Okay, so it's almost taking 3.5 times as long, if you want to think of it that way. Now, part B says how many times greater is the radius of the larger tank than the radius of the smaller tank. So if you think about it, we're talking from the center of the tank out to here is the radius, and then from the center of this tank out to here is the radius, and we're interested between the ratio of those two things. Okay, so we kind of already have our 3.375. So let's think about what we know about capacity. Well, we know the volume of this one, so we'll call the volume of the large and the volume of the small. So if we think about it, if we were scaling up from the small, we would say that the volume of the larger one is going to come from, if we have a scale factor of k, if this ends up being k times that r value, we talked about how the volume will actually have a factor of k cubed. And so you can see now we have volume of small over volume of large. Well, if you think about it, what we're trying to find is the scale factor. So we can divide both sides by the volume of the small. And what we would end up with there is we'd have volume large over volume small equals k cubed. Well, if you think about it, this volume large and volume small, that's the same thing we just found here. So what is that ratio? That ratio is 3.375. So I'm just going to move this over, and we're going to say 3.375 is equal to k cubed. So how would I isolate what k is? Well, to undo a cube, I'm simply going to take the cube root of 3.375, and that's going to give me what k is. I'm just going to do that quickly with my calculator, and I get 1.5. So I get 1.5. And so how many times greater is the radius? Well, there's a scale factor. It's 1.5 times greater. And so again, the focus here is that how is volume related between scaling? Well, it's related by a factor of k cubed. So that was it. In summary, the key idea is if two 3D objects are similar and their dimensions are related by a scale factor of k, then the surface area of the similar object is going to be k squared times the surface area of the original, and the volume of the similar object is going to be k cubed times the volume of the original. What you need to know: if you know the dimensions of a scale diagram or model of a 3D object, as well as the scale factor used to enlarge or reduce it from the diagram or the model, you can determine the surface area and the volume of the enlarged or reduced object without determining its actual dimensions. All right, and that's it.